What's up everybody, welcome to another video, and I hope you're ready to flex those brain muscles. In this video, I'm going to talk about the binomial theorem. So I'm going to explain the formula a little bit. We're going to look at some patterns like Pascal's triangle, and then we're going to go through a couple of examples, and hopefully this helps you. I know for a lot of people this formula is really intimidating, including for me when we first see it, so hopefully this helps you be a little bit more comfortable and make it a little bit more intuitive. But before we get right into it, I want to mention a couple of things. First of all, I only have a couple of videos left until my pre-cal playlist is done. So that means I have most of the stuff covered in a pre-cal class in videos on my channel in my pre-cal playlist. So if you're studying for your final exam, go ahead and make sure to check out my playlist. Maybe you'll find some stuff that can help you. You can see some examples, get some stuff re-explained, that sort of thing. But the next thing I want to mention, in case you want something more than just videos, is that I partnered up with a company called Ansari Math. This is a one-on-one online tutoring service. They hire tutors from universities like UC Berkeley, UCLA, UC Davis, so pretty legit universities if you ask me. And these are math majors who can tutor from basic math all the way up to multivariable calculus. So if you want some one-on-one tutoring and you click the link in the description, you'll get a session for free. So there's no risk involved. You can try it out and see if you like it. Maybe it'll help you prepare for your final exam. So let's go ahead and get into the video, the binomial theorem. So this is the formula, but first I want to kind of talk about the motivation. Why do we care about this theorem? That's always a cool thing to look at, right? Why do we care? Well, let's look at this example, x plus 2 squared. This is pretty easy to expand, right? We can write it out twice. We can use that 4-letter F word, FOIL, first, outer, inner, last, combine the like terms, then we get this expanded, right, polynomial. What about x plus 2 to the 5th? This is where it gets really tedious because look, we can write it out 5 times. We can FOIL out the first 2. Now I have to distribute. Then I'm going to have to do that again 2 more times. Terrible. Not fun is the conclusion, right? This equals not fun. So although this formula does look intimidating, it actually makes our lives easier because we're able to expand binomials like this a lot easier than if we were to do this. And this is just to the 5th power. Imagine if it were to like the 9th. It would take you a page and a half of work to fully expand that. Here we can do it in just a few lines. So believe it or not, this formula makes our lives easier. So now let's quickly talk about the formula a little bit. X, Y, and N are all fixed. In other words, that means we get X and Y from the terms inside of our binomial, and N is just the exponent, right? So we have all those things, we can plug them in. The only thing that's changing is K, and this is kind of what we're using to do our iterating, right? We're starting at 0, that's our first term, then 1, 2, 3, all the way until we get to N. And since we're starting our counting at 0, we're going to end up with N plus 1 terms, which makes sense because here we have squared and we end up with 3 terms. 2 plus 1 is 3, right? So here we can expect 6 terms, the first being an x to the 5th term and the last being a constant term. So hopefully that makes sense. Now we're going to look at something called Pascal's triangle. So what Pascal's triangle helps us do is it helps us get the values for this thing right here, which is often called the binomial coefficient. I usually say it out loud as n choose k. You will see this in other contexts too, like probability and combinatorics and stuff. And there even is a formula to evaluate these. N factorial over n minus k factorial times k factorial. Although Pascal's triangle helps us find these values a lot easier than working out this formula a bunch of times. And I'll show you exactly why. So Pascal's triangle, here we have 1, 1, 1, 1, 2, 1. So the pattern is that on the ends we always have 1s. And how we can get all of the entries in between the 2 ends is we can just add the 2 entries directly above, right? So 3 equals 1 plus 2, 3 equals 2 plus 1, 4 equals 1 plus 3, 10 equals 4 plus 6. That's how we can get every entry, and we can repeat this pattern however far we want, right? So this is why it's so helpful, is because what we can notice is that 1 is equal to 0, choose 0. 1 is equal to 1, choose 0, and 1, choose 1, right? So each of these rows corresponds to a set of binomial coefficients. And if we label them row 0, row 1, row 2, row 3, etc., then the nth row corresponds to n choose 0, n choose 1, n choose 2, all the way up to n choose n, which is exactly what we need to expand binomials using this formula, right? So in the example we saw before where it was x plus 2 to the 5th, our n would be 5, so we would go down to the 5th row, which is down here. So this would be 5 choose 0, 5 choose 1, 5 choose 2, etc., all the way to 5 choose 5. These would be all of the binomial coefficients we're going to use to expand that binomial. So we can get them all by just writing out this triangle and going down to the row we need to go down to. We can get all these values without having to do this formula over and over again, or even really worry about this at all. We just use the triangle. So I think that's why it's so helpful, is because it does make it a lot quicker, in my opinion, than trying to do this over and over. So this is what I'm going to use in the examples moving forward, but I want to point out one more pattern before we get to the first example. So what I've done here is expanded a few binomials, but I've kept them in pretty general terms just so we can kind of see all these patterns come together. And the first thing I want to see is if we can identify those rows from Pascal's triangle, right? Those binomial coefficients. This is to the second power. That corresponds to the second row, which is 1, 2, 1. Here we have our 1. There's a sort of invisible 1 out in front, right? 1, 2, 1. Third row, that's 1, 3, 3, 1. And we see that here, 1, 3, 3, 1. Fourth row, 1, 4, 6, 4, 1. So we're seeing them show up in these expanded binomials. One thing I want to mention though, that does not mean that the final coefficient for this term is just going to be 4. Because if y is like a constant and not just a variable, we're going to simplify, right? We're going to multiply that out. Like if y is 2, we're going to be left with 8. So I just want to point that out. But this is a great place to start. Then we can simplify from there. And we'll see that through an example. If that doesn't make sense yet, it hopefully will pretty soon. The next pattern, and really the last one I want to point out, has to do with these exponents, and this comes directly just from the formula. Since we're iterating by k, we start with k equals 0, we go up to 1, 2, etc. until we get to n. So that means that our first term is always going to be x to the n minus 0, which is just x to the n, right? So x squared, x cubed, x to the fourth. And what happens through each term as we increase k, the exponent for x decreases. Here we go, x squared, x to the first. We can think of this as x to the 0, which is equal to 1, right? And what happens to y is it increases. Here we have y to the 0, y to the first, y to the second. And that pattern is consistent throughout all of these. Let's look at this. X to the fourth, x is going down by 1 throughout each term. Third, second, first, 0. And y is going up. Y to the 0, 1, 2, 3, 4. So putting all of these patterns together, kind of the goal of noticing all this, is being able to expand a binomial without even really having to think that much about this formula. And hopefully that's what we're going to be able to do through a couple of examples. Let's go and get to the first one. All right, so here's our first example. We saw this in the beginning of the video. Now we're going to officially expand it. And it's not too bad. We'll do a little bit harder of an example next. But how I like to start is just first drawing out Pascal's triangle, because I want the fifth row. That's going to give me all of the binomial coefficients that I need to expand this. So I'm going to go down to the fifth row. So 1, 3, 3, 1, 1, 4, 6, 4, 1. And let's see, remember we start counting at 0. So 0, 1, 2, 3, 4, so I need one more row. This is going to be the row I need. 1, 5, 10, 10, 5, 1. There we go. That's all of the binomial coefficients that we're going to need. So we can just erase all this because we don't need any of this. We just need that fifth row. All right, so in our first term, we're going to have n choose 0. That's 1. And remember, if we're comparing this to our formula, our n is 5. Our x is just x, our y is 2. So we have 1 times x to the fifth times x to the fifth times 2 to the 0, which is just 1. So I can really erase 2 to the 0 and the 1 out in front, right? So our first term is x to the fifth, which we should have expected. Maybe you already saw that coming. Plus, now we have a 5 times x to the fourth. Remember the pattern? The powers of x are going to decrease throughout each term, and the powers of 2 are going to increase. So I'm going to have 5 times x to the fourth times 2 to the first. And now we can continue this pattern by using these numbers and this pattern. We can continue this without even having to really look at the formula. That's why I like noticing these patterns, because next we can just say, okay, well, let's put the 10 there. let's do x to the third, and let's do 2 to the second, right? Next, I'm going to have to use another row here. Our next term, well, now x is going to be squared, so we're going to have 10 times x squared times, and now 2 is going to be cubed, plus, now we're going to have 5 times x to the first times, and now 2 is going to be to the fourth, plus, now we're going to have 1, x is going to be to the 0, so that's 1, and we're going to have 2 to the fifth. So see how easy it makes it when you just kind of write out the first couple of terms and notice these patterns. I didn't have to go plugging stuff in. I didn't have to calculate a bunch of different coefficients or like do anything like that. So now let's just simplify this and we should be done. So the first term is just x to the fifth. The second term, 5 times 2, that's 10. 10x to the fourth. And this is what I meant earlier by like, these aren't your final coefficients. You may have to simplify. This is what I was talking about. 2 squared, that's 4 times 10, that's 40x cubed. Plus, now we have 2 cubed, that's 8. So 80x squared. Plus 2 to the fourth. That's 16 times 5, that's 80 again. 80x plus 32, right? 2 to the fifth, 32. So this is our fully expanded polynomial. We've expanded this binomial into this polynomial. Hopefully that process makes sense. Let's do another example. All right, so here's our next example, 2x minus y to the fourth. We're going to expand this. And I encourage you, pause the video, try this on your own. If you're trying to prepare for an exam, test yourself, see if you can do this, and then press play to check your answer. So I'm going to start out the same way, which is writing out Pascal's triangle. We want to go down to the fourth row, but I know that the fourth row is going to be 1, 4, 6, 4, 1. So I'm just going to kind of skip ahead and write that out since I just wrote it out and remember what the fourth row is. Hopefully you know how to get to that point though and get that fourth row. So now we have our binomial coefficients. What I want to point out about this example and what makes it a little bit tricky is let's notice what our x, y, and n are, right? So our n is clearly 4. Our x, in this case, is 2x, but our y is actually negative y, right? Because here we have a plus, here we have a minus. So we could sort of think of this as 2x plus negative y all to the fourth. That's how we're treating this, right? So my terms are actually going to alternate between positive and negative, and you'll see why in just a second once we start expanding this. So I'm going to start with 1. I'm not going to bother writing that because it's going to be 1 times 2x to the n, which is 4, and I need those parentheses because that fourth power is going to go to the 2 as well, right? Times negative y to the 0, which is just 1, so that's my first term, plus now I have a 4 times 2x cubed. Remember, these are going down by 1, and my negative y is going up by 1. So now I just have a negative y to the first, plus 6 times 2x squared. Remember, I need the whole thing to be squared, and now we have negative y squared. Plus, I'm going to have to use another row here. 2x to the first, well first I need this 4, and then 2x to the first, and then negative y cubed. And now my last term is going to be 1 times 2x to the 0, that's 1, times negative y to the fourth. So let's see if we can simplify this a little bit. And why our terms are going to be alternating is notice that whenever we have negative y to an odd power, so 1 as well as 3, then that negative is going to come out in front. It can join the constants that are going to be out in front, and we're going to have a minus, right? But whenever we have negative y to an even power, like 2 or 4, that negative is just going to go away because we're multiplying by a negative an even number of times. It's just going to go away. So that's kind of why we end up with these alternating positive and negative terms. So my first term is going to be 2 to the fourth, which is what? 16 let's see, I'll write an equal sign here, equals 16x to the fourth. That's my first term. And then remember, we need this minus. It's going to be a minus. And you could write a plus and then go back and like erase. If you don't notice it right away, that's fine. But this minus is going to come out in front. 2 cubed is 8. So we basically have -1 times 8 times 4. And that makes our constant out in front. Hopefully you're seeing where I got that. -1 times 8 times 4. That's 32. Well, -32. We brought the negative out in front already, right? So 32, x cubed y to the first. My next term I know is going to be plus, but again, if I wrote a plus and it ends up being minus, I have an eraser. It's all good. So plus 2 to the fourth. First, notice what I'm doing is first I'm kind of identifying what constants I'm going to be able to bring into the front, putting those together. Then I'm just going to have x squared and y squared, right? So this is going to be 2 to the fourth. 2 squared, that's 4. I'm jumping ahead. 4 times 6, that's 24. So 24 times x squared times y squared, because this negative goes away because it's squared, right? So 24 x squared y squared plus, am I going to be able to fit all this on one line? We'll see. So now I have 4 times 2. Oh, and see, I did it. I wrote a plus. Should be a minus. That's why I have an eraser. Minus 4 times 2 times -1. I already brought the negative out in front. So we're just going to have minus 8x y cubed. And our last term is going to be plus because we're raising -4 to an even power. Sorry, -y to an even power. I keep jumping around in my head. Plus y to the fourth. Hopefully this is what you got. Hopefully you worked it out in advance and the negatives didn't mess you up too much, but this is the fully expanded version of this binomial. I'm actually going to throw in one more example. We commonly see this example come up. I want to make sure I cover it and kind of give my take on how to approach it. Then we'll finish up the video. So here's our last example. This is a very common kind of question to be asked, which is to find the coefficient of a certain term. So we're going to find the coefficient of x to the 6th and the expansion of x plus 2 to the 10th. So really what this is asking us to do is when x is raised to the 6th power, right? When we expand this, whichever term has x to the 6th in it. If we expand this and simplify everything, what is being multiplied out in front of x to the 6th, right? That's what it's asking. So where that's going to come from is this binomial coefficient piece as well as this y to the k piece. So here's the way I approach it. There's different ways to do it, but n is 10 and x is being raised to the 6th power. That means that n minus k equals 6th. So I can find k. What can I subtract from 10 to get 6? Well, 4. So if k is 4 and n is 10, then this binomial coefficient piece out front is 10 choose 4, and that means that y, which is 2 in this case, is being raised to the 4th power, right? Not too bad. Now from here, if you have access to a calculator, you just punch this in, multiply it by 2 to the 4th, and you're done. If you don't have access to a calculator, you have two options. You can write out Pascal's triangle and go down to the 10th row. It's a bit tedious, but it'll get you this number, and then you can multiply it by 2 to the 4th, which is 16, right? Or you can use the formula, which is what I'm going to do right now. I'm going to use the formula, which says that n choose k is n factorial, which is 10 in this case. So 10 factorial over n minus k factorial, that's 6 factorial, times k factorial, that's 4 factorial. And remember, factorial just means we're multiplying all the way down to 1. That's the way I think about it informally, right? So 10 factorial is 10 times 9 times 8, all the way down to 1. 6 factorial, 6, 5, 4, all the way down to 1. So we can get some nice cancellation here. Because if this is multiplying by 10 all the way down to 1, and this is 6 all the way down to 1, then we can divide out 6 and beyond from this 10 factorial. Hopefully that's making sense, right? Since this is 10 times 9 times 8 times 7 times 6, right? From then on is just 6 factorial. So let's divide that out. And what we're left with is 10 times 9 times 8 times 7. We divided out 6 and beyond. And 4 factorial is just equal to 4 times 3 times 2 times 1, but I'll leave out the 1, we don't need it. 4 times 2 is 8, right? So we can cancel 4 and 2 into 8. 3 goes into 9 3 times. So we have 3 times 7, that's 21, times 10, that's 210. See how easy it is? You don't need a calculator. This is equal to 210. And that's probably quicker. I mean, I did it fast because I've done this 100 times, but it's probably still quicker than going to the 10th row, just in this case. That's only because we're finding one term. If I had to fully expand that, then I would definitely go to the 10th row because I'm going to need all of those coefficients. Hopefully that makes sense. So 210 times 16, that's going to give us our answer. Let's go old school here. 6 times 0, 0, 6, 12, carry the 0, 0, 1, 2. So that gives us 0, 6, 3, 3,360 is our coefficient, all right? See, don't need a calculator. So hopefully that made sense. If you can use a calculator, just multiply it out, do that. If you want to go to the 10th row of the triangle, do that as well. Whatever gets you to 3,360 is the way you should do it, the best way that you understand it. So hopefully this video helped. Hopefully it made sense. Good luck on your final exams. Check out my Precalculus playlist. Make sure to check out ansarimath.com. Click the link in the description. Get yourself a free one-on-one tutoring session. And most importantly, keep flexing those brain muscles, and I'll see y'all later.